Good morning, good afternoon, good evening, depending on the time you are listening or watching this video. Because it's EL 316 electric circuit theory 2, Department of Electrical and Electrical Engineering, University of North. My name is A.R. Professor A.R. My liege in the University of West here, my liege at my parents' university, also the second one. Then you have my research grades, my Google Scholar, my Orchid, and my YouTube channel. This is the course outline for EL 316, Electric Circuit Theory 2. We're supposed to cover non-linear circuit analysis, network synthesis. We'll start with network synthesis. We're going to be using three books. So I will share the title of the books for you so that you can be able to access them. To start with is my own book, Towards Understanding and Expertise in Applied Electricity, Part 1, Fundamentals of Electrical Engineering Made Simple. We use this book in Electric Circuit Theory 1 extensively. It will still be useful. The second book is Network Analysis and Synthesis by F.F. Kuo. We are going to be using that too. And
two important topics within the domain of electric network theory are network analysis and network synthesis. We assume that the reader is familiar with the elementary methods of network analysis. How does network synthesis differ from network analysis? To answer this question, we require definitions
using words that invoke an immediate recognition on the part of the reader. Three such words, which are used extensively in describing the behavior of electric networks, are the network, the excitation, and the response. An example of the identification of the network, excitation, and response is given in Figure 1. Let us see that Figure 1. This is figure 1. Excitation is the input. Excitation can be called input, it can be called action, it can be called excitation, and then the output is known as response. It can be called reaction, it can be called response. And then the network is the network we are talking about. Like I normally said in class, the excitation is the input to the network, while the response is the output. Let's continue reading the definitions. On your own, you are still going to read this in more detail. The word network is used to describe a collection of elements connected or coupled together. The three passive elements are the resistor, the capacitor, and the inductor, including the transformer. These elements are idealized elements in that they are assumed to be lumped, linear, finite, passive, and bilateral. The word excitation is used to describe a source of electrical energy to be connected to the network. Two energy source idealizations or active elements we shall deal with are the constant voltage source and the constant current source. Several other terms are used interchangeably with excitation, such as driving force, applied voltage, current source. The response of a network can be a particular current, a charge, a voltage across some element, or combination of elements. The energy dissipated in a resistor, a ratio of voltage magnitudes for sinusoidal excitation, e.g., two forms of response of importance are the time response or time domain response, meaning the variation of some response with time, and the sinusoidal frequency response or frequency domain response. What are they saying here? You know, we can work in the time domain and we can work in the frequency domain. So we can have time domain response, we can have frequency domain response. Please, in electrical engineering, we're interested in definitions. When we ask you to define or explain what you understand by certain things, you'll be able to explain it to us. These words we have just used to describe electric networks have counterparts in practically all areas of scientific study. A wide variety of physical and biological phenomena may be described in terms of an action called a stimulus and a resultant reaction called response. When a stimulus is applied to an organism, the response may be physical movement, chemical change, or both. The stimulus of an electric current in the leg of a frog causes muscular movement. I will not be reading line by line for you. You are supposed to be doing the reading. I'm just raising the curtain for you. If the network and the excitation are given, if the network and the excitation are given, and the response is to be determined, the problem is defined as analysis. So network analysis means when you are given the network and you are given the excitation and you are asked to find a response, that is known as network analysis. But when the excitation and the response are given and it I want you to read more from this book.
On these definitions. On these definitions. So the problem of synthesis is that you are giving the excitation, you are giving the response, you are to determine the network. That is network synthesis for you. I hope you are going to read more on that. So I want you to read chapter 1 here very well. I cannot read everything for you. You are supposed to read. Yeah. There are network equilibrium equations that you are supposed to know by heart. To start with, you have equation, I think there is equation. What did they write in equation 1.1? Okay, let's leave that one. You are supposed to remember a resistor. This is a resistor, one of the passive elements. I is the current, V is the voltage, and the voltage is known as, what they are writing here is for a resistor, you have the current, I. For an inductor, you have the voltage. No, for an inductor, you have the voltage. Okay, yeah, sorry. What they are writing here is the voltage across a resistor is Ri, R multiplied by I. The voltage across an inductor is L d dt. The voltage across a capacitor is 1 over C integral IT. On the other hand, you can write formula for current. The current through a resistor is GV, where G is the conductance. G is the conductance. G is the reciprocal of R. For a capacitor, the current through a capacitor is C dV dt. The current through an inductor is 1 over L multiplied by that. You can also talk in Laplace transform. Now, if we are in the frequency domain, the equation 1.2 and 1.3 are time domain equations. You can see that we are using small letter to represent current, I. We are using small letter to represent voltage, V. So in the time domain, we normally use small letters to indicate the voltage. I hope you are hearing me. You are hearing me now. Okay. Now, so equation 1.2, equation 1.3, equation 1.2 and 1.3 are time domain equations, and we use small letters. So, but when we get to frequency domain, we use capital letters. So equation 1.7 and 1.8 are the frequency domain equations. So we're now using capital letters. I for current, V for voltage. The element remain the same, that is resistance, inductance, and capacitance. This one do not change, but it is the current and the voltage. So in the time domain, we say in bracket T, that it is a function of T. In frequency domain, we say bracket S is a function of S. So in the time, sorry, for the voltage, it is Ri. For the current, it is LSI. For the resistor, Ri. For the inductor, LSI. For the capacitor, I over CS. That's voltage for current like that. Now, if you go to table 1.1, it's showing you certain things. It gives you the symbol of a resistor, inductor, and capacitor, and it's giving you all those equations. In the time domain, the first equation is the time domain. The second row is in the frequency domain. And for the impedance means opposition to current. The impedance of a resistor is simply R. The impedance of an inductor is Ls. The impedance of a capacitor is 1 over Cs. The admittance, which is the reciprocal of impedance, the admittance of a resistor is G, which is 1 over R. The admittance of an inductor is 1 over Ls. The admittance of a capacitor is Cs. Please, with this, I think I want you to study this chapter to the end of that chapter. The end of that chapter. Let me just scan through. I'm scanning through for you up to let me scan to the end of that chapter for you. You can get these books have already been shared on the course platform. In this chapter, you are being reminded about two-port network. Please study this chapter to the end of that chapter. It gives you further reading. It gives you some problems to try to handle. Now, chapter 2 is network analysis that we have done several times. So you can revise it. Let me go to FFQ. Let me go to FFQ, the second book. In this book, for this course, I want you to pay attention to the following chapters. Chapter 1, look at chapter 1, it's a general chapter, look at it. And after that, you can move to, I'm coming. You can also look at chapter 5, which is network analysis, do revision on it. Don't forget to revise Laplace transform. Laplace transform, don't forget to revise it. Cannot escape it. Then we can then go to chapter 10. Chapter 10, chapter 11, we're going to do a lot of business with chapter 10, chapter 11, chapter 12. We're going to do a lot of business with it. Let's go to chapter 10. Let's go to chapter 10. That's on page 290. 290 here. think I'm already entering. Let me look for the beginning of chapter 10. Okay. Elements of realizability theory. What are they discussing here? Ladies and gentlemen, you should know that for every network, we can have mathematical expression that represent it. Every network, every element, every system has a mathematical expression that can describe it. But not every mathematical expression can be realized as a circuit or network. Are you getting the gist? Every element, every system has mathematical expression that will describe it. But not every mathematical expression can be realized by a network. So we talk about realizability theory. I think we will have time to discuss this in more details. So let this be our video 1, is an introduction. But before we even conclude the introduction, I want to encourage us, based on my book. I normally want you people to restudy the preface to my book. In my preface, I encourage you to always practice. You will see in the preface where I said the first component of the teaching methodology adopted in this book is learning by steps. The first component leads to understanding. The second component of the teaching methodologies is encouragement for practice, which leads to expertise. Practice makes perfect. It's a recommended adage. At starting, the student is encouraged to follow recommended steps. The steps are internalized by the student through practice. The student will become expert, may not need the steps, and may even develop shortcuts and faster approaches. To fully understand what is taught, a student must practice, 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 and practice. So this is an engineering course, you have to practice. So that's why I've encouraged the class to be divided into groups. It will be a study group. So 5 students in each group. You're expected to, this is not history that you can lay on your bed and be reading. You have to be on your table to actually practice. So we end this first video here. This will be the first video. This will be the first video for our online lecture, ELE 316. It's an introductory video. So this is video 1. We'll tag this one video 1. Thank you for having me. I hope to make this video available on my YouTube channel, and you can have access to watch the video. So yeah, I wish us a successful semester, but everybody must be up and doing everybody has to work out. Thank you. I thank my team who have supported me in this exercise. So we can stop here for video 1.